and encourage policy as well as behavioral change. We first began to address PFAS and firefighting foams at the end of 2019. And so this event today is a milestone in what is our second phase of the AFFF project. It's an opportunity for ACAP and Finland to share the results of their project work. Finland's been leading this project for ACAP, and the United States has been a contributor and co-lead of this project in parallel to the work you'll hear about today. And in the United States, we are working in Alaska and scoping work in Canada to transition AFFF stocks out of remote Arctic communities. Our work there follows recent changes to the U.S. military specification that requires U.S. military sites and installations to transition away from AFFF to non-fluorinated foams. So this gave us the opportunity, and through the ACAP project, we are currently developing simple guidance on how to identify AFFF in small communities, whether that be in fire trucks, wagons, barrels, or small extinguishers. And we're working with the Alaska Department of Environmental Quality to support their AFFF replacement program, where communities can be reimbursed for removing and transporting AFFF to collection facilities. And we're working to help safely destroy the AFFF stocks through various methods, including supercritical water oxidation and incineration. We've just started to remove AFFF from communities in the Aleut Islands, and we'll soon be collecting AFFF from single collection points in 2 different communities that will serve as hubs for a number of regional communities. So we're very excited about what we're going to learn about today, which is more at an industrial scale, and what we're doing in Alaska and Canada, which is more at a community scale, and it really follows what ACAP specializes in. So we are finally working in Alaska to identify an airport and a facility in Alaska that we can pilot transition away from AFFF to non-fluorinated foams, and we'll have more updates on that as it progresses. So with that, I look forward to our discussion today, and I'm going to turn this back over to my esteemed colleague, Timo.
Thank you very much, Patrick. And now I would like to give the floor to Niall Ramsden from ENRgConsultants UK, who was the original drafter of the ACAP transition manual a couple of years ago. Please go ahead, Niall.
Thank you, Timo. Hello, I hope everybody can hear me, and good afternoon, good morning to you all, wherever you are in the world. My role today is really just to give a little bit of background to the application of firefighting foam for those of you who are not totally familiar with it, and also a bit of an introduction to a document I'm being very proud to be involved with. That's the Arctic Council transition manual. Just a quick bio. I've been around a long time, as most of you can probably see in the screenshot here. In fact, it's only just realised in September this year I've had 50 years involvement with foam. 50 years ago I actually joined the firefighting foam company and worked in the UK and the USA with a couple of those companies. 30 years of that career though has been in as a totally independent from any supplying company, but the fact that I know foam from being at the other side of the fence many years ago, I know the tricks of the trade and how to sort of make a demonstration look good rather than an actual really test. I've been a member of the NFPA 11 Foam Systems Committee. For those who are familiar with it, that's a US-based committee that specifies how foam systems should be designed, not where they should be used, but how they should be designed if you decide to use one, and also the European norm equivalent to that standard. One of the things I'm involved with right now is the NFPA Research Foundation Transition Roadmap. It's a working group of 4 people with other help from other people sometimes as well, developing a transition roadmap guidance mainly aimed at municipal fire brigades. That's an ongoing thing, but I think we're just phase 3, updating that as well. One of the main issues though is on a project called something called LASTFIRE, which is a group of around 20-25 international oil companies. All the big guys are there: ExxonMobil, Shell, BP, Total, Petronas, Saudi Aramco, all of these sort of companies who work together in developing best practice in storage tank fire hazard management. Well, the last 5 or 6 years of that project has been focused almost entirely on the transition to PFAS-free foam. It's not all just theoretical, because I was actually an advisor to one of Europe's biggest thermal fire, where some of you remember it, it's actually 20 years ago now, a terminal called Buncefield in the UK, about 23 tanks more or less simultaneously ignited, and very heavily involved there on the foam application and logistics. Interestingly enough, it was at that time where this issue was just arising, and a lot of 3M foam was donated to the incident. People were glad to get rid of it. There was actually a big debate at the time between the Environment Agency in the UK and the local authority fire and rescue services who were tackling the fire, about whether they should actually use foam or just burn it out. In the end, it was really a political decision to use the foam, recognising that the public had to be made aware that you could actually manage such incidents. But a more recent claim to fame is I was lead author with my company ENRgConsultants for the Arctic Council AFFF transition manual. So a bit of background. So I'll show you this little Pathé News video from the 70s. This was probably one of the first introductions of PFAS containing foam in the early 70s. I wasn't actually at that demonstration, but I do recognise some of the people in it. It was actually done by Angus Fire, and I recognise my boss a few years later from that incident. So it was from that demonstration. So it was one of the first demonstrations, and it wasn't AFFF, as it's called. It's actually fluoroprotein foam. Sometimes we forget that PFAS compounds are used in more than just aqueous film-forming foam. So why were the new foams so much better than the previous types? Well, the big issue about them was that the previous types, which mainly relied on a protein source for their manufacture, had no fuel tolerance whatsoever. So if you mixed up the foam with fuel, basically it just disappeared and the fire restarted. So it's very important to apply these foams very gently. So that was a main issue. PFAS compounds, made these foams fuel resistant, and actually it's a protein-based foam that was the first PFAS containing foam called a fluoroprotein foam. The PFAS compounds also made the foam much more flowable, so it helped it go around hot objects and seal against them in the middle of a fire. So they had big advantages. They also managed in certain foam concentrates to cause an aqueous film, as it's called. So this is really not water, it's foam solution. That's the foam concentrate you buy mixed with water to make foam solution. It made a very thin film, and a very, very thin film of foam solution float on the fuel under certain circumstances, depending on the surface tension of the fuel, the surface tension of the foam solution, and the interfacial tension. But so it could actually get a very thin film, and that thin film, aqueous film, the foam solution, gave very, very fast knockdown in certain circumstances. Not all of them. It was very well marketed by some companies as if it's the answer to absolutely everything, but there were some problems associated with that foam as well. But it undoubtedly became the industry norm. And the main one, although I've already mentioned fluoroprotein foams, the main types are aqueous film-forming foam, hence AFFF. So essentially, these PFAS compounds made foam application much easier and more effective. It made it incredibly easier for a firefighter because of their fuel tolerance. They could actually get away with bad application in many circumstances. So the first question anybody who is responsible for emergency response would ask when you said, okay, we can't use PFAS containing foams, do the new types work? Can you make them work? Now, let's not forget, those of us who have been in the industry a long time, there used to be foams that didn't contain PFAS and they were made to work. So we shouldn't forget that. So really, straight away, we should know the answer is yes, but we had to prove that again. There are two main independent sources of information. One is LASTFIRE, that group I just mentioned to you. A lot of different tests being done. And the other main source of information on an independent basis is United States. Well, it's no longer DOD, of course, it's a DOW work that they did. That work is described in a lot of publications, but of course, because it's aimed at rapid rescue in aircraft crash fires, that type of thing, the concentration of the work was on Jet A type fuels and very thin, shallow spills of that type of fuel. Obviously critical to life safety, but a completely different situation from the industrial types of fire incidents that we tend to be talking about in LASTFIRE. So that's the sort of work that they were doing. You can see, very rapid, 2 minutes response time, very rapid application of foam. It's a life safety issue. It's not really an asset protection issue. And I say a lot of that work, well, all that work has been published, and indeed within the Research Foundation work and webinars I've just mentioned, there are some presentations if you go online about that work. The person in that picture there is a guy called Jerry Back, one of the colleagues on the NFPA Research Foundation working group. He made the comment, legacy foam application techniques work fine with the new foams. However, we haven't taught them for years. The AFFFs and the fluoroproteins made firefighting much, much easier, and maybe made us a little bit lazy about training to do the job properly, applying the foams very gently. So that's the US Department of War work. LASTFIRE has done probably nearly 1,000 experiments now, ranging from just a 2.5 meter diameter tank up there in the top left, which is a standard test, been around for about 20 years. It's a test to assess the capability of a foam to work for the special circumstances of a tank fire. In fact, right now I'm in Hungary doing a few more tests with some new firefighting foam concentrates, ones that are being developed for use at a very low concentration, only about 1%. So this work is ongoing. But we've done an awful lot of tests, different application techniques, different fuels, different fire scenarios, you name it, we've done them. Just to give you a couple of examples, these are, I think, 17, 18 meter diameter tanks. These are obviously speeded up, I think, about 4 times. This is some work we did in France. We've done work in Saudi, France, Hungary now, Spain, all sorts of different countries and different locations. This particular piece of work was trying to demonstrate or try to assess what's the best application technique for a tank fire. Was it best to apply the foam at the side of the tank, or was it best to sort of fire it across at 12 o'clock in the middle of the tank? So that's that sort of work. In fact, if you look in the background there, here, this pit here is actually 50 meters long by 6 meters, and we built that in conjunction with a facility that's LASTFIRE. And we actually proved here that we were using these PFAS-free foams traveling 50 meters. Now, if you read the standards say foams can only travel 30 meters under their own momentum. So you can see we're actually doing a lot of work that really maybe we should have been doing before, but nobody ever bothered because it's too easy almost to use PFAS-containing foam. That's me just posing at a fire in Saudi Arabia, but the point is they can work, even in very hot climates like Saudi Arabia. And indeed, I know there's a lot of firefighters out there now doing an incredibly good job controlling some of the incidents that are happening with the current circumstances. So we proved they can work. The next stage is how do we implement change from AFFF to PFAS-free foams? And that's really where the Arctic Council phase-out program, the associated transition manual that was developed and training modules, that's where that comes in. Now, okay, it's the Arctic Council that did the work, but realistically, that work applies to every single application of foam, whether it's for a local authority, municipal brigade, or a large industrial brigade. The principles are described in that document are applicable to every single incident. The key objectives were to develop cost-effective, and at the end of the day, everything has to be cost-effective, and appropriate recommendations for the removal of PFAS-containing foams for all applications within the Arctic region. And this is important without jeopardizing risk reduction, especially, of course, in the aviation industry, rapid rescue situations, that type of thing. And as I pointed out, although we've specified the Arctic region there, in reality, the work applies to every single foam application in the world. And the other point was to arrest at the time legacy issues. So in other words, you weren't using any more. So it start introducing interim measures, which several countries have already adopted, of course. You can't use these foams, the old foams, for testing or training, that type of thing. It's a very, very pragmatic approach. We'd quite like to see. We can be very theoretical and academic about this, demanding all sorts of things. But ultimately, these foams had to be used by practical people. So it's important to make sure that the process is practical. The transition process itself is described in the manual. If you actually look at the manual, it looks very daunting to begin with, because there's a protocol for every single aspect of this transition. But once you get it down to the ones that you need, then it becomes a very workable solution. First step is always, hey, do we really need foam? And if we're honest about it, there's probably quite a lot of places where, well, does the risk really justify the expenditure of that foam system? I can name places, no end of facilities where if you look closely, you think, well, why have you put foam in there? Just because it seemed like a good idea, or it's easy to put something in that is, they know the risk doesn't justify it. Having decided you're going to go ahead, yes, the next step is obviously to identify those systems that do need that transition and identify the site-specific or system-specific or application-specific modifications required, following by procuring new foam and equipment, and then, of course, cleaning out equipment from the old stuff, whether it's storage tanks, pipe work, application equipment, wherever, installing and commissioning the new equipment, and finally, something that the industry had been very bad at, whatever foam they've been using, make sure that on an ongoing basis there's proper assurance to make sure those systems will continue to work. We have not been good at that, if we're honest. We really haven't. For every section of this, there are different protocols explaining what it means and how you can do it. And of course, everybody has to do this under something like a management of change to show that even during the process, you're not risking risk reduction. So you need a proper fire risk assessment to begin with. Then when you get to identifying what you need to do, you develop the applicable protocols. And I said I don't know, I've never recounted them, but there must be 50 or 60 different protocols in the document. So if you want to clean out a foam chamber, a device that pours foam onto a storage tank, it describes that process. Then, of course, you've got to specify the replacement equipment in detail, and it's a very good opportunity to do a proper procurement specification. Too often in the past, people didn't put a performance-based specification together. They just asked the supplier, please supply me some foam. Well, that's not good enough. Every application has special characteristics that require special characteristics from the foam concentrate. Then, of course, cleaning out the equipment and disposal of the equipment and the liquids, as Patrick just mentioned, and there's good news, there's more and more techniques becoming available, making them more competitive and practical as well. And then, of course, commission new equipment, and then make sure that the insurance procedures are in place, site-specific emergency response procedures are in place, and most importantly, the training, because these new foams do need proper training using real fuels at proper training grounds. And of course, during all of that time, you've got to have interim risk management as well. So all of that is described in the transition manual. Right now, today, of course, we're going to concentrate on some of the work done by my colleagues on this webinar, case history of cleaning out that equipment. So we're in that phase. Just to mention, though, that the document also includes some training modules about how to use the foam, the background of the situation, some of the protocols, that type of thing. So it's a very comprehensive document. So that's where this comes in. And I'm very proud to have been involved with it, working with Timo and his colleagues. But I would say it's a very comprehensive transition guidance, and the training modules are very valuable as well. And make the point again, it's applicable to all sectors, whether it's municipal, aviation, or industrial. Just to make another point, this manual's been out there for a few years now, but it has been proven in pilot cases. Personally, I've worked on ones in Australia, United Kingdom, and other countries. And of course, today we're going to hear about some pilot cases carried out in Finland. So with that, what I would say about this whole situation is that this is actually an opportunity to do things properly, because maybe we haven't been doing things properly with phone systems in the past. So it should be seen as an opportunity, not a crisis. So with that, thank you all for listening to me, and I look forward to listening to my colleagues now describing that pilot study I've just mentioned. So thank you very much.
Thank you, Neil. And that was a reminder for us that there are also other issues to talk about and think about than just the residual AFFF concentrations. Now, I will give a quick rundown of the actual pilot project that we did. As soon as I get the slide there. Yes, so the project was called Testing the Arctic Council Transition Manual. So we decided that because there was this manual, we decided to see whether it would work. And we received funding from the Finnish Ministry of Foreign Affairs to do this, and we had 6 months for the project. So, I mean, a lot of things could have been made differently, but we were really limited with perhaps more limited with the time than funding at this point. But anyway, the scope of the project was really to look into this guidance in practice. And I'd also like to highlight that because I'm a policy person myself, so I was really interested in trying to figure out this interface between the authority requirements for these projects and what is actually possible to provide in terms of analysis, etc. So we decided to test this manual with 2 foam containers in these 2 fire trucks, and Jaakko will explain this part of the project in a few minutes. And the second part of it, and this is very much related to the Arctic conditions, because we wanted to know at which point on-site wastewater treatment would become feasible, because large quantities of PFAS containing wastewaters are formed during this cleaning process, and regularly we would be taking that water to high temperature incineration in Finland. But in the Arctic, we know by experience, especially in the most remote Arctic territories, that transport distances are so high that this might not be possible. It's true that some of these wastewaters that were formed in this process had to be treated otherwise anyway, because they would contain solvents or anything. But the big question is really that, can this overall volume be made smaller? And perhaps most interestingly, and this was something that I don't, there's been a lot of academic and other studies made of these cleanup processes and so on, but we didn't really have an answer to the question that once we actually treat this water, could it be released to the municipal sewer system or even to the environment? Because this would be the case in some remote regions, and what limits for this release should be used. And then, and this was a very, very small part of this project, but we did have some study material from the airport hangar, this sprinkler pipe, and we did study the PFAS contamination in it, as well as tested a couple of potential cleaning methods on whether they would further remove the PFAS residues in the internal surfaces of this pipe. But one of the big things here was that even though this sprinkler pipe has been in use and it has been loaded with AFFF foam, it has also been rinsed since then. And the fact is that the initial concentrations, because these pipes do not contain foam all the time, and they are rinsed after testing, so the concentrations that we were able to analyze from the internal surfaces of this pipe in the swipe test were relatively small. So it wasn't like we weren't really hopeful that the tests that we were going to run with the pipe would turn out like huge removal rates. And of course, there has been a lot of academic and other studies made on how what techniques you should be using with these pipes. But as I said, this was sort of an additional part of this. And then, of course, one of the things that we were really interested in was that, and this was the question was really coming like if I was the authority who was in charge of trying to figure out whether this system has been cleaned in accordance with the best available techniques, what would I need? What could the company or the consultant, whoever was working on this, what could they give us? So we took quite a bit of samples from different parts of this project, and different analytical methods were used. First of all, we had these surface sampling systems, which were, for example, for the internal surfaces of both the tank as well as the sprinkler pipe. And we analyzed the target PFASs and also total oxidizable precursor assays. And then we partnered with FREDSense, who has been developing this rapid analysis technique in Canada, and Blake will give a presentation on that later on. So the question has been around in all of the foam cleanup webinars and meetings that what do you need to prove that the system is clean? Like, and another question is, what can you have? Like, what sort of measurements are actually available? So, and of course, regulations matter. And in the EU, we have both the REACH regulation, new foam, PFAS foam restriction, as well as the POPs regulation restrictions, for which this guidance for transitioning and really interpreting what this legal definition in accordance with the best available technologies could mean. And the legislation contains limit values for the concentration of PFAS in the mixture that you can use. This is what is called unintentional trace contamination in the EU legislation. And of course, the cleaning must ensure that those limit values will not be exceeded in the future in whatever foam is going to be put into the system. What is also interesting is that the same requirements always apply, the same concentration limits, irrespective of whether the extinguishing waters are used in systems whether the foams are used in system where the extinguishing waters would be collected, or whether they would be used in mobile fire trucks that could release the foam into the environment directly. So this is clearly something that, although we have some transitional periods for these limit values, but they don't make a difference between these two cases. And then we also wanted to calculate these PFAS masses, like how much PFAS do we actually have remaining in the system, because that gives us a good perspective on, like another perspective to these concentrations. And with this, I will finish my introduction, and I will give the floor to Jaakko, who will run you through the fire truck cleaning process. Go ahead, Jaakko.
Thank you, Timo. First, I share my screen. Okay, now can you see it well? Okay.
Yes,
so,
we can see. Yeah.
Okay, good. So hi all of you. My name is Jaakko Valtonen, and my presentation is about this Arctic Council transition manual and clean out protocols piloting test work that we done last year. And 3 years ago, I retired and I founded my company Farsol, and now I work as an independent fire protection consultant. And before that, I worked in different municipal and high hazard industry emergency management roles as a firefighter, as an incident commander, as a deputy chief fire officer, and lately as a corporate advisor in terms of fire and explosion hazard management. And during that time, when I was in emergency response and fire brigade, so I did use a lot of forms. So we used a lot of forms during decades, and we used the forms in flammable liquid fires and trainings. At that time, we still had the chance to train a lot with forms and also with testing. So I'm guilty for spreading PFAS on the environment, but my excuse is that we didn't know the issues at that time. And then I had the privilege to be a LASTFIRE member for 18 years, and during that time I had a chance to participate also the firefighting foam fire tests that Mr. Ramsden Niall mentioned earlier, and involving the developing and implementing the test protocols. Actually, the picture here is from large scale fire tests in Vernon, France. And now with my company Farsol, we have successfully cleaned out over 40 foam systems and over 40,000 liters foam concentrates, and much more rinse waters has been sent for high temperature incineration and that way destruction. So in my presentation, I will explain how we did these tests and what were the results. And these tests were made in cooperation with Lassila & Tikanoja Industrial Cleaning Services. So first one will be the airport fire truck cleanout tests, and then military fire truck cleanout tests, and finally the foam spray system pipe cleanout tests. So this airport truck foam tank capacity was 1,300 liters, and it was made from glass fiber polyester. And the concentrate inside was Tamex AFFF foam concentrate with high PFAS levels in it. And we used the Arctic Council vehicle cleanout protocol, and basically the one cleanout cycle was that we filled the foam tank with fresh warm water. This time we used the water temperature was 50 degrees Celsius, and it stayed inside for 30 minutes. And then next we drain out the water, then high pressure jet wash the foam tank, and then the cleanout protocol states that if there's still some foaming or the drained material doesn't meet the PFAS limit, then the cleanout cycle should be repeated. And in this test, we did this cleanout protocol cleanout cycle once, and on top of that one cycle, we did also Farsol cleanout method. And there was two reasons for that. The first reason was that we had done with this method already several fire truck cleanings with excellent results, and we agreed with airport operator that we will continue with that same method also with other fire trucks. And secondly, the reason was that we could test how the glycol solution would enhance the cleaning results. So we used 20% water glycol solution at 50 degrees Celsius temperature, and the soaking time was 60 minutes. And after that, we circulated the solution through all foam piping of the truck and back to the tank for 10 minutes. Then we drain out the solution and did a pressure wash. And then last rinse with cold water. So we took samples from this first clean-out round. We took 2 surface swab samples and 2 liquid samples. So 1 surface swab sample in the very beginning of the clean-out process, and then first liquid sample after we have filled the tank with warm water, and then surface swab sample after pressure wash, and then also liquid sample after pressure wash. And then 2 additional samples after this second clean out round with water glycol solution. For sampling, we used 3 times 100 milliliter bottles, and for surface swab samples we used IPA moistened sample cloths, and the surface swab area was 100 square centimeter, as seen here. The Eurofin's food and feed testing laboratory in Sweden did the analysis with these methods mentioned. You can see here the methods of target and topaz analysis. So the results of the liquid samples were that already after the first rinse and soaking, the total PFAS concentration had decreased by 99% from the original concentrate levels. And if we look at the diagrams of those results, we can see that we have here the 3 liquid samples. So the first one, 2A, is after first soaking with warm water, and second one is after pressure wash, and the third one is after glycol soaking and high pressure wash. And the numbers here and units are nanograms per liter. And we can see that here liquid sample 3, so here in the middle, we only could get 6.2 FTS levels out of the analysis, and that was because the 6.2 FTAP levels, so capstone P levels, were so high that we couldn't get any other individual results of that. but we can see that from the first sample to the last sample, the PFAS reduction was 42%, the PFOS reduction was 54%, and 6,2-FTS capstone A was 9.5%. So these were the target concentrations. And then when we look to TOPA concentrations, we also can see good results in the last sample that shows that the levels of PFAS and PFOS and 6,2-FTS has went down quite significantly, but interesting here is that the TOPA levels in liquid sample 4 PFOA TOPA levels are higher than in the first sample. So that way, with this final glycol soaking and pressure wash, we still get something. Yes, sir. Something.
Morning. Hey, Wendy sent out a note last night that she was.
Go ahead.
Okay. Yeah. Okay. So then when we go to the surface FAP results, we can say that the container was already so clean after first rinsing that concentrations exceeding the UTC values could not be dissolved into new foam. And if we look at the diagrams here, so we have 3 surface FAPs here. First one right after emptying the container and light rinsing. Second surface FAP sample was after first hot water soaking and high pressure wash, and the third swab was taken after glycol soaking. So here we can see the reduction of PFOS from sample 1 to sample 2 already 80%. And 6,2-FTS level from sample 2, from sample 1 to sample 2, 94.9%. And also more reduction was achieved from second sample to third sample. So still 53% reduction in PFOS and 66% reduction in 6,2-FTS. And then we also calculated what could be the maximum rebound level. And we used a result of surface FAP samples for that when we found that the highest concentration was PFOS, so 40 micrograms per kilo. And then the mass, when we calculate, so the mass in the sample area was 0.03 micrograms. And then when we calculated further to the whole surface area of the tank, the total mass of PFOS could have been 21 0.6 micrograms. And when the tank capacity is 1,300 liters, the maximum rebound level could be only 0.016 micrograms per liter. And the UTC limit for PFAS is 25 micrograms per kilo. So there would be any problem with the rebound either, according to these test results. So the conclusion of this airport fire truck clean-out test is that in this case the cleanup procedures in according to AFFF base out in the Arctic and this vehicle clean-out protocol, those were efficient and sensible practical way to implement in practice. So what we did was actually that one washing cycle included warm water fill, drain out, high pressure wash and sample. And this cycle should be repeated so many times that an adequate level of purity is achieved. And based on the surface swab samples, as we saw, the tank would have been sufficiently clean out already after the first clean out cycle. But when we continued with the glycol solution, then the PFAS levels were further decreased up to 66% with the 6.2 FTS. So we could say that repeating the washing cycles and using glycol or other appropriate solvent would enhance purification and cleaning results, but other things like cost effectiveness and overall appropriateness should be considered on a case by case. And this point is highlighted also in the clean out protocol. The challenge here in the piloted method is to verify the PFAS levels from a sample taken after the clean out cycle. And on basis of that, we should decide whether to continue the cleaning or not. And this time when we took the sample, it took 7 weeks while we got the analysis results. So in practice, that would be too long time to wait for the results. So today we can hear about an on-site quick test that we could get results within hours, and that would help the decision making during the clean out process. And then the military truck clean out tests. So now we had a smaller foam tank and the tank material was different. It was stainless steel. And again, removed foam concentrate was AFFF foam with high PFAS levels. And this time we used the water temperature was 30 degrees Celsius for 30 minutes. And then we did this clean out cycle. So we drained the water out, then the high pressure jet washed the internals of the tank. And then we repeated this cycle 3 times. So first sample was taken right after the foam concentrate was drained out. And then we took liquid sample after each clean out cycle. So 3 samples altogether. And then we took the last swab sample after last rinse. Why we took only 2 swab samples was because the area to take the sample was very limited, because we only had this little opening on top of the tank. So we had to take the surface sample around this opening and from the top of the tank. So we only took the sample in the beginning, very beginning, and then after the clean out process. Yes, we used the same sampling method and same analysis. And now again, in the first sample, the 6,2 FTAP capstone P concentrations were again so high that it was not possible to determine other individual PFAS levels. Only 6,2 FTS could be measured, and that's why we have only FTS levels here in this diagram. In the second sample, we got the measure from PFAS, that was 12 nanograms per liter, and other concentrations were already below the limit of quantification, so below 10 nanograms per liter. But here we can see a good reduction of 6,2 FTS levels from the first sample to third sample. And then the results of those 2 swab samples. As mentioned, we should keep in mind that the samples were taken only from the roof top, so in which the foam concentrate has not been in continuous contact. But anyway, we got the results that showed 6,2 FTAP reduction, 65%, and FTS reduction 70%, and also PFAS reduction 17%. Again, we calculated maximum possible rebound level, and the result was as low as 0.03 micrograms per liter. So well below the UTC level. Again, these vehicle cleanout protocol procedures were efficient and sensible practical way to implement in practice. And based on the surface swab sample, the tank would have been sufficiently clean already after the first clean out cycle. And again, the same issue was here, that after one clean out cycle, we should have the results to make a decision to continue or not. But of course, this time we couldn't get that result, so we just repeated the cycle 3 times and waited for the results. But as we saw from the results, we could have been stopped after first cycle, according to these results. Okay, Timo, do we still have time for this foam spray pipe clean
Well,
test?
we are running a little late, but I mean, if you run this through quickly.
Okay,
That's
I
all right.
tried. So what happened was that foam concentrate and water entered in the pipework in February 25, and that was because of fault in the system. And as Timo mentioned, the pipework was rinsed out with fresh water immediately after detection. So the pipework is normally dry with open nozzles, and total length was 300 meters, pipe material stainless steel, and total volume of pipework 1,600 liters. So we took one 6 meter long stainless steel pipe for the test, and it was cutted in 400 millimeter long sections for the tests. And this time we used this foam spray system clean out protocol. Actually, there is also foam solution pipe clean out protocol and foam sprinkler system clean out protocols available, but basically the same. The clean out cycle is the same for all of those three different protocols that could have been used in this test. But anyway, the one clean out cycle is that the pipework will be filled with warm water over 25 degrees Celsius. Drain it, take a sample, repeat if necessary. But the protocol does not say how much above 25 Celsius the water temperature should be and how long it should be stay in the pipework. So what we did in the tests, we used 5 different methods and three time periods as follows. So first one was soaking in water at 20 degrees Celsius for 1 hour, 4 hour, and 24 hour. And same time periods for soaking in water at 50 degrees Celsius. And the third one was soaking with glycol solution at 50 degrees Celsius. So we didn't remain the temperature because that wouldn't be the case also in real world when doing this. We also did a test just rinsing the pipe through with cold water, and we also used very high pressure cleaner at 700 bar pressure. Okay, and when the soaking time was completed, the surface swab sample was taken. And then we also took target and TOPA samples from soaking water that was remain in the measuring cylinder. And the surface swab samples were also taken of tap water rinse and high pressure wash. So when we evaluate the clean out test results here, with all used soaking methods, after 1 hour soaking, the 6,2 FTS concentration surface samples had decreased from 95 to 99%. So in comparison, to the reference samples taken before the tests. And soaking time of more than 1 hour did not significantly improve the cleaning performance. And 1 hour soaking with 20 degrees Celsius water alone reduced already the 6-2 FTS concentration by 99%. The lowest measured concentration of 6-2 FTS in surface swab sample was reached after 4 hours of soaking in propylene glycol solution. So summary of the foam spray pipe clean out tests. Again, the procedure protocol was efficient and sensible practical way to implement. The pipework here used in the test was normally dry and flushed right after the activation. Therefore, the PFAS levels were already low in the reference samples taken before the tests. And this applies actually for all the tests, and it's mentioned in the transition manual that the procedures are generic in nature and outline the steps required to clean out the equipment, but cannot be specific in terms of the actions taken, as these will be different in every installation. The intent is to use the outline guidance and develop a specific procedure for each installation, depending of the PFAS exposure and configuration of the system. Okay, I think that was it, and I'm open for any questions. Thank you.
Thank you. There are a couple of questions on the chat already, but I think we will leave them in the Q&A after the presentation. So we will now have Antti's presentation, Antti Seppälä's presentation on the water treatment. Please go ahead.
Okay, thank you. And I hope you can now see the right screen.
Yes.
Yeah, let me put camera on. So my part of the task was the on-site wastewater treatment. So in short, testing the Arctic Council transition manual in practice for the water treatment part. A bit about my background. I have about 23 years of experience from different contaminated soil, groundwater remediation, industrial wastewater treatment, special cleanup projects during the course of these years. First 15 years I was employed by a company called ACAP. Then roughly about 8 years I was a solo entrepreneur in my own company called Engwater. And now once again from the beginning of this February I'm back in a bigger gang, so now working for a company called ENRgConsultants. But this project together with Jaakko and Timo, we did it back on my Engwater days. Before starting, I identified 4 main targets for my task. First was to have more quantitative and qualitative data on the waters that would be treated. So gain knowledge on the volumes and on the PFAS concentrations of the wastewaters formed in different steps of the clean out, or as I like to call it, decontamination process. Then, of course, the feasibility of the on-site water treatment, test pre-selected treatment methods in practice and analyze the results to select different water patches suitability to the on-site water treatment. Then, of course, to take a look at the regulatory limits, compare the reach effluent concentration levels to existing regulatory limits, or if there are, but anyways, having the discussion on on what kind of levels can be reached and what kind of levels should be applied for this kind of activities. And then, of course, from idea to concept, as Timo mentioned, there are faraway places that if we need to decontaminate a AAAF system, then it will be quite expensive task to transport all the waters to high temperature incineration. So these were the 4 targets that we identified. A few words about the practical arrangement. As Jaakko and Timo already mentioned, 2 fire trucks containing concentrates were cleaned. Of course, drained first the concentrate and cleaned. Using pressure was warm water and glycol water mixture. Then the cleaning waters were all collected in separate IBC containers from each cleaning phase, so that we can keep them separate in order to gain specific knowledge on each step and the concentrations that end up in the water from each cleaning step. A water sample was taken from each wastewater batch, both for target and TOPA analysis, and then also selected parallel samples were sent to FREDSense for on-site screening test. Blake later will tell more about the results on that part. And unfortunately, as Timo mentioned, that we had some like 6 months time to do the task, but we did it in a way that we carefully planned for 4 months, and then in 2 months' time we needed to do all things in practice and get reports ready to meet the demands of the schedule. So unfortunately we didn't have the chance to analyze first and wait for the analysis data, but instead we did the treatment right away on the spot after having the actual clean out. And then, of course, the treatment was done in order from expected lowest concentration to highest contamination. We see later from the results that how well we managed in that. There's more detailed information about the treatment process later, but it basically consisted of 3 different adsorbents in small sequential filter columns. You can see a glimpse of the filter columns on the picture on the left. Initially we had plans that we would have a bigger system and also bigger wastewater volumes, but as it turned out that we were not able to get the bigger volume, so we needed also to scale down the equipment used in the practical tests. And the test sample and the protocol. As Jaakko already explained, but this in more detail, or in relation to the actual treatment, how we worked with the samples. So we had the 2 separate trucks, first the airport truck, and then secondly the military truck. And from the airport truck, we collected 4 different water samples: first rinse, second rinse, third rinse, and a final rinse. And then from the military truck, truck first rinse, and then the second and third rinse were collected together in one IBC container. And then the treatment itself, as mentioned earlier, from lowest to highest expected influent concentration, one batch at a time. So here I try to explain the if you take batch 1, I ran it through granulated activated carbon filter, then a specific proprietary resin, and then ion exchange. And then the same procedure was done for each batch in this order that they are presented here. And as the last batch, I actually did a combination. So earlier here, I didn't use all the waters from each batch, but there was some leftovers from each batch. And then as a final batch, I wanted to see that what would be the concentration if I combine all those batches to one combined sample, and finally did the treatment for that. And then the results, what we look later on, are numbered from 1 to 7. So they are equivalent with the batch number, but of course in a way that they all went through the whole treatment train. The samples in total, we took more samples that we finally analyzed, and this was because of having limited budget. So we took 7 influent samples. They were collected from the IBC containers after mixing the contents, so making sure that it's well mixed and the sample is representative. Then we collected 1 effluent sample after each treatment step, but unfortunately we didn't have the budget to analyze all the samples. So finally we analyzed only the effluents after the final treatment step, that in this case was the ion exchange resin. And then, as mentioned earlier, 8 samples were sent also to FREDSense. There were parallel samples taken from the influent or from the effluent from the same sample point at the same time. And all samples were taken from sample bottles provided by the laboratory, using, of course, powder-free nitrile gloves when taking the samples. 3 times 100 milliliters were sent to Eurofins, and 3 times 1,000 milliliters were sent to FREDSense. Then the treatment in more detail. Each batch volume was from 300 to 1,300 liters, as Jaakko told that the airport truck tank was 1,300 liters, so that was basically the maximum amount of water that we got from the batch when we filled the tank full to the top. And naturally only the water batches were treated, so the glycol water mixture was collected and sent to high temperature incineration. There is no sense in trying to treat a glycol water mixture with these selected treatment methods. On average, we had a very low flow. Of course, we had small amount of total wastewater volumes to treat, but anyways, then again very low average flow because of the design of the system. It was a small system, but when doing the design, I wanted to make sure that I would actually get the breakthrough in the system. So I wanted to have the adsorbance volumes very small. And that, of course, resulted to very low flow. The empty bed contact time for the carbon was on average 15 minutes, which is, I think, the minimum advised for carbon. And then empty bed contact time for the resin and eye exchange mass was on average 4 minutes, which is again about the same that is suggested. I think it's 3 minutes, but anyways, because the reaction kinetics is a lot faster. And this is also signified in the picture. So here the arrow showing the granulated activated carbon, of course, there were several columns containing carbon compared to the proprietary resin and ion exchange to tune in the whole treatment train to match the needed empty bed contact times. And as mentioned, start from the lowest expected concentration, going to highest in purpose, of course, not to overload the adsorbents in the very beginning, and then hopefully in the end have the possibility to test the breakthrough with higher concentrations. Then about the analysis, Jaakko already showed basically the same figures, but this of course is not from the cleaning point of view, but from the water treatment point of view. So this is the order that I actually did the treatment, and there are some practical reasons that I wasn't able actually to wait for the military truck water. So once we were ready with the airport truck, I started the treatment right away. So that explains that, okay, there is lower concentration here. But anyways, we are going towards the higher, more or less. And this sixth sample here, or batch, containing 1.5 million nanograms in the target analysis was actually the very first rinse after having drained the foam concentrate from the tank. So this was actually before, more or less before the first fill up of the tank with water. So, and therefore, as expected, this was very high concentration. And as Jaakko already explained, that we had an issue with few of the TOPA analysis because of the very high 6.2 FTAB concentration. So that interfered our analysis, and we actually then, due to that, we had very high detection limit for these two samples. And then difficult to get to right. Now, then the effluent data calculated from the influent and effluent, we basically had 100% reduction in the first 3 samples. And then actually this is very exciting to see, and as mentioned, Blake will later on show more in detail the difference of the analysis data that we gained from using different methods and different laboratories. So, but what I'm showing here that if I take the analysis results from Eurofins, I had 100% reduction still after fourth batch. But if I take the US EPA standard analysis data, then I have 92% reduction rate. And then, of course, there is a huge difference if we take a look at the target or if we take a look at the TOPA analysis. I think in order to save time, it's not worth to go in detail through all the figures, but as mentioned, you will get the material. So later on, you can study them in detail. And then if there should be any questions, of course, we are more than willing to answer. A few words about the conclusions. I think we have more conclusions coming later on after having all the presentations, but a few from my point of view. First of all, taking a look at the previous page, it's quite obvious that the target analysis is not sufficient to prove effluent cleanliness. So the TOPA reveals unknown precursors in effluent and influent, and then of course it's a good question that okay, if we use oxidation as it's used in the TOPA method, what happens? So we most likely actually break down some precursors, and then we find new components. And I think Blake is already anxious to show, but he has more detailed comparison between the analytical methods, and that actually indicates quite a lot of differences between methods and laboratories. So a question from my point of view is that, okay, what method should be used, and sort of like who to believe when defining if the system, or specifically from my point of view, when the effluent is clean enough. Then another question is that what's clean enough? But this is one lesson learned. And then a few overall conclusions on the on-site water treatment. Anyways, taking a look at the results, I must say that on-site water treatment can be combined with these cleanouts, and it can be made technologically and economically viably. And even very high concentrations, so up to 100,000 or even more than 100,000 nanograms of PFAS concentrations can be treated using selected water treatment technologies. Might be these ones that were tested or some other ones, but anyways, it can be done. And also at the same time, I can say that for these suitable concentrations, the on-site water treatment is cost efficient, all costs included, if we compare it to high temperature incineration. And obviously the cost efficiency is increased if the volumes increase, or if we are very, very, very far away from the treatment plant where to send the waste to be treated. And then finally, if we have a rapid on-site analysis for PFAS, that's very useful tool to be, first of all, used to study when we have the breakthrough in the treatment train. And secondly, or firstly, depending on how you want to think, to analyze the influent concentrations to choose between on-site or high temperature incineration. treatment. Because if we take a look at the results, if we reach 1.5 million nanograms, it might not be wise to use adsorbents, but if we stay on a level of 300, 400, 500,000 nanograms per liter, we can still do it. And then finally, the regulatory limits. Discussions with the municipal wastewater treatment plants actually showed quite a lot of variations in interpretations that what kind concentrations, if any, are acceptable to be discharged to the municipal sewage. So basically, so far, because we lack the limits, it depends on which wastewater treatment plant you ask. Some might say that, okay, there is no limit, just put it into the sewage. And the other one says, no, you need to be below detection limit. So in order to make sure that, okay, this is a functioning concept, of course, we need to have the PFAS limits set, what we can discharge, either to the municipality or if we discharge to the nature. And then another one is that, okay, there is a permit topic that needs clarification. If we do this on industrial side, what permit we actually should apply, if any? I don't have the answer, but that's one big question raised during the test. That's all from my side. Thank you. So as Timo mentioned, maybe questions then later.
Yeah, thank you, Antti. And Blake is already eager to start his own presentation.
Yeah.
So go ahead, Blake.
Yeah, thanks. I'll just pull it up here. Is that visible to everyone? Does that look okay?
It is.
Perfect.
Yep.
Well, thank you, Timo, and thank you, everyone who's spoken before me. It's a really good bunch here, so I'm excited to be a part of this and part of the project. I forgot to do my bio slide, so I'll just say a little bit about myself on this one. So I'm Blake Farris. I'm Business Development Manager with FREDSense. I've been a part of the PFAS industry for about 5 years and becoming kind of more tied to the AFFF transition industry in about the last 2 or 3. So really excited to be a part of this group and chatting with you today. So today I'm going to talk a little bit about field screening for PFAS, and I'm hoping to kind of cover 3 main questions during the presentation. The first is kind of how we should be thinking about PFAS analytics when you're doing an AFFF foam transition. Also, what if you could test PFAS at your site? What does that actually mean? And then lastly, we're going to talk a little bit about kind of that burning question of how does field screening actually compare to the other analytical methods that you see so commonly. So we're going to dive right into that first question. And so when you're building your AFFF transition program, it can feel a bit overwhelming, honestly. There's a lot of considerations that you need to make, like what parts of the systems need to be clean, what process you should follow, and how to treat your waste, and kind of the things everyone's been talking about here already. And, kind of cherry on top of that is, what PFAS analytical do you need to use for your situation? And so there's a bunch of different methods that all come up, different acronyms, but broadly speaking, you can kind of divide them into 2 main categories. The first are kind of those speciated or targeted methods. So these are those gold standard methods used to find individual PFAS species. They find anywhere from about 25 up to 100 or so individual compounds. But with there being thousands or tens of thousands PFAS species, that's kind of only the tip of the iceberg when you look at those methods. And then you have the total methods. So these are methods that see all the fluorine ions in your sample, or they use kind of a additional oxidation to find some of those hard to see PFAS, those fluorotelomers that you hear about, and I'll talk a little bit more about later. So that allows you to see, a lot more of the PFAS loading in your system. And so now the big question becomes, how do you pick between these methods when you're going to an AFFF site? And so picking the right method for your project can be difficult. Both the speciated methods and total methods have strengths and weaknesses to them. So the speciated methods are kind of best for risk assessment. So answering the question of what PFAS are there today in those end chains, and answering like, does your process kind of match the current regulations, particularly in North America? In the EU, you see also total methods being used as part of the regulations, and also understanding what chain lengths you're seeing. So it's really about understanding what that current PFAS load looks like right now and fitting those parts into kind of your regulatory compliance frameworks. So those are all kind of great questions that speciated methods can help you answer, but it's also missing a bit of the larger slice of the PFAS problem that can then be seen with the total methods that are giving you kind of a different perspective. So they're there to identify those hidden PFAS that are kind of, from the iceberg analogy, they're below the surface. So those ones that speciated analysis can traditionally miss. So total methods can help you kind of look into the future. So what is your total PFAS loading? Will there be any surprises down the road from those other fluorotelomer compounds? And it also helps you look really deeply into your treatment effectiveness. So speciated methods will miss things like the ultra short chain PFAS, those PFAS with carbon lengths of 3 or less, as well as fluorotelomers that come from foams. So all of these are kind of important things to think about when you're confirming PFAS cleanliness in your system and during a clean out. Oh, sorry, I jumped a few slides. So, that kind of begs the question of why is this difference between speciated and total methods really important? And so when you're looking at foams, the foam makers do not just use the regulated and speciated PFAS that you can see during those tests. So our team has reviewed over 50 SDSs from foam manufacturers, and every SDS that mentions PFAS has some things in common. They all have some sort of solvent in there. They all have a blend of fluorinated substances. So this could be those PFAS that you see in a speciated analysis. It could be different PFASs. And they also have the fluorotelomer surfactants. So those are more PFASs that aren't your typical speciated analysis PFAS. So you won't see them in your speciated analysis, but over time, they will transform into regulated PFAS compounds from the environment, from interacting with temperature and soil and other things throughout, the foam's life. So that means if you're only looking at a speciated analysis, you could be missing a major portion of your PFAS loading. And that's why, in the EU, you see regulations that also look at total PFAS while using speciated as another reference point for that analysis. And so that kind of looks at that first question. So, how should we be thinking about PFAS analytics when doing an AFFF foam transition? Consider using both speciated and total methods during your transition. speciated, kind of important for that current PFAS loading and how regs might impact you today. Total is really important for learning kind of the lifetime cleanliness of your system and whether that's been kind of fully completed during your AFFF transition. And now we'll jump into what if you could test for PFAS on your site. So that's a question that we ask kind of everyone we can. I know all the speakers here have probably heard me ask some form of this kind of question to get an understanding. And some of the common answers that we have heard when you ask about field screening and what might change is, first of all, you can make proactive decisions in the field rather than leaving it to a judgment call. You can expedite your timelines instead of waiting weeks for results. You just wait hours. For our AFFF cleaners, you can validate when your cleaning is below those cleaning thresholds in the rinsate. For our treatment operators, seeing when your system has breakthrough and making on-site decisions to keep your system operating smoothly. For anyone who's kind of a site owner, an airport, or an oil and gas facility that's working this, it's really kind of about reducing equipment downtime so that you can get an operation up and running again quickly. So, kind of that 3-week turnaround makes it so that site owners kind of holding their process up until they get those results and they get the okay to refill their PFAS systems or their foam systems with the new fluorine-free foams. And using on-site testing is really about complementing your laboratory analysis. It's not so much about replacing it. It's so that you can feel confident when you're sending that regulatory sample that your system's clean or that your treatment system is operating efficiently, so that you don't get those surprises down the road. So that's why we kind of built FRED PFAS. It's really so that you can get data on your site and make your decisions with confidence. And it's about a briefcase-sized lab in a box that allows you to measure PFAS in a few hours. And so how does it work? It's total PFAS measurement, meaning that it'll see both those fluorinated compounds, PFAS, that you're worried about from the regulations, and also those pesky fluorotelomere surfactants that don't appear until it's kind of too late. You've already cleaned out your system and it comes back in a wave there. So FRED PFAS itself measures down to 1,000 nanograms per liter of total PFAS, making it kind of perfect for the transition process and the understanding there. And you get your results in 4 to 5 hours of grabbing your sample all the way to seeing a result on our screen. And your team will follow a simple kind of 5-step process after you collect a sample through to results. And so that's how we've kind of built field screening and been able to bring it to site and see those results for PFAS kind of closer to real time. So that kind of answers that question around, what happens if you can actually do PFAS at your PFAS testing at your site. So data-driven decisions, confidence in your process, and real-time adjustments all become kind of a reality rather than a wish for those out there. And so now comes kind of the juicy question of how does field screening actually compare to other analytical methods, the lab? Can we actually make decisions based on, a tool that's on site? And so this is kind of similar to the visual representation that you saw from Antti's presentation during the treatment process, except with the addition of the green labels for where the FREDSense samples were taken. Like Antti mentioned, we took 8 for us to then look at. So since we weren't able to make it out to the project in time, these samples were grabbed by the on-site team and sent back to the FREDSense lab for both in-house LCMS testing, both speciated and TOPA analysis, as well as running these samples on FRED PFAS. And so the samples were collected both from the cleaning process as well as the treatment process that Jaakko and Antti have kind of already talked about. So first we'll take a look at the rinsing samples from the tank cleaning following Jaakko's process that we saw earlier. And these are the first and second rinses from both of the trucks. So here are the results from the 4 samples. You kind of see there's 4 columns, which represents each of the samples. In the blue, we have the speciated analysis from both labs. In the orange, we have the TOPA. And next to them is the green, which is 3 FRED PFAS runs on these same samples. So as you can see on the graphs here, FRED PFAS is trending with the lab analyses. So if they go up, FRED PFAS goes up with them. And when it goes down, FRED PFAS also goes down with them. And so it lands somewhere between that speciated and TOPA super consistently. And only for that kind of final rinse on the right side do you see FRED PFAS kind of match closer and higher to TOPA as we approach the detection limit of our device. And so some of the key things that you're seeing in the data here is that for the airport truck in rinse number 2, you can see that it's not yet below that threshold limit with both the lab and the speciated, the TOPA, and FRED PFAS kind of in that same area. And so this definitely, when you look at it, requires another clean. And Jaakko obviously did. I think he did 3 or 4. I think he did 4 on this truck. So definitely good to keep going there. And then the other part is that when you look at the combined military truck rinses, we see that all the FRED PFAS and lab results are all kind of below that 25 ppb threshold limit for some of the PFAS species. And that kind of allows you to see it kind of in real time, how on-site screening can kind of help a transition project. And so when you're cleaning a truck, FRED PFAS is a great indicator of what you would see from the lab. And now we'll jump forward over to the treatment side with Antti's work. And so we're talking about those cleaning rinses running through the treatment of GAC, resin, and ion exchange to be cleaned for discharge down the road, Antti's system that he talked about earlier. And so after the treatment process, we see that pretty much all the PFAS levels are lower than they were in our last graph. And so once again, you're seeing that FRED PFAS is following that same trend with the lab data closer to TOPA in this case. And so once again, it's blue for the speciated, TOPA for the orange, and green for FREDSense testing. And you will see that they all kind of move together up and down based on how effective the treatment was. And so 3 of the samples that we received, you really see that those levels are low. I have 1 part per billion marked on the graph there. So the speciated analyses are all well below that number, while the TOPAs kind of sit all in that same area, just under about 100 part per billion total TOPA. And so that's pretty good treatment out the back end of the system there. And then lastly, with the exception of 6IE, which was one of the first rinses from the truck, super heavy PFAS loading for a smaller treatment system, you really see that breakthrough on site in the speciated, the TOPA, and that FRED PFAS on-site analysis. So you can definitely use FRED PFAS to detect breakthrough before you're discharging your water into the POTW or wherever you're discharging from your project. And so for those who really want to deep dive into the results, I've added a table here for you, same ones that you'll see in Antti or in Jaakko's presentation. So that'll help you dig a little bit deeper to understand how each of the methods compare to each other. So the highlighted results, each one that's highlighted the same color, they match up to each other. So you can see kind of how effective the treatment was and what kind of happened both FRED PFAS wise and lab data wise. And FRED PFAS is kind of showing that similar movement in each of the cases. And the breakthrough from 6IE was detectable with FRED PFAS, which is, I think it's super neat. So really exciting there. And that kind of answers that last question of how do you compare, how does field screening compare to other analytical methods? So it trends closely with the lab data, and it's trending closer to TOPA than to the speciated analysis, showing kind of more of that total proxy than just PFOA or PFAS number. It really gives you that full picture during your AFFF transition. So some of the lessons that we learned during this process is that in-field screening would be a useful tool during transition, whether it's breakthrough, confirming your PFAS loading before it goes into your treatment beds, or confirming the cleanliness of your AFFF trucks after the cleaning procedure. And we also noticed that really high PFAS samples require a dilution to work in FRED PFAS. So there's an upper limit to FRED PFAS that you then need to dilute after. You can use some indicators like foaminess of the samples, rinse numbers, and sample location to help you make those dilution decisions. And then FRED PFAS is, again, trending closer to those TOPA results as an indicator. So it allows you to see that future contamination from the fluorotelomers and confirm the cleanliness of the system during your AFFF transition. So I'll just say thank you to everyone who's stuck around to the end of the webinar here. I believe I'm passing it over to Timo for a bit of a wrap up, and then hopefully we can fit in some Q&A.
Yeah, this is not the end of the webinar yet. So thank you, Blake, and I will now finish with sharing the wrong screen. But now you should be able to. All right, you should be now able to see my concluding remarks, right? Is that correct? Perfect. So
in PowerPoint mode, not like it's just, I don't know if you want to go presentation mode or not.
Oh, yeah. I get it. I don't know what happened. Well, this is not how I wanted to end the time. I'm just gonna do it the way I did it earlier. So I really wanted to just, and I want to remind you all that I'm looking at this from the point of view of enforcement authorities. Actually, although we are not technically an enforcement authority, but right, now you should be seeing it. No. Well, I don't worry about it. So just to conclude, I think what this test did convince us that these clean-out procedures that were presented in the guidance were efficient. And again, it's stressed that each system is different, so you really have to tailor the approach every time. And one thing that was also obvious that when you repeat the wash cycles or use the glycol or other appropriate solvents, it improves the purification, but then it also gives you a bigger amount of waste. So this is something that you have to balance with. And the big question, as I think we also saw in the comments already, was that how do you prove that the system is cleaned? Like, first of all, the documentation is critical, because that is how you prove it to the enforcement authorities that this is what we have done, and we can see how this could be done without chemical analysis. In this project, we were able to analyze quite a large number of samples. I would say that it's probably more than you would normally do in a similar project, and it was good for following how the cleaning process developed, but sometimes the results could even be contradicting. Like we had this FTAB measurement after a couple of rinses. But of course, this will depend on how much you know about the system, about the phones that they were. The airport truck was from 2003. The military trucks was newer, but the airport truck certainly has had like several layers of older foam, so it was not surprising to find PFAS there. One of the issues that we struggled with was that sample turnaround time was really high, as Jaakko mentioned, 6 to 7 weeks. Another conclusion is that we could not comply with the EU requirements completely with just the target analysis, because we need to take into account the precursors as well. Now the big question is, of course, that could this rapid screening method, which went along with the TOPA analysis quite well, could it be accepted as something that you could replace fairly expensive laboratory analyses? That's something that should be discussed or decided by the relevant authorities. We found the swab tests useful to analyze the residual contamination, although there are questions that are related to this. I think there was one question on the chat on this, that how do you know that it's actually a representative sample, considering that all the different layers and formations in the container could cause increased PFAS residues. And then this issue of whether the PFAS contaminated waters can be treated on site. Like municipal sewer PFAS limits should be set for the right PFASs. Now in this case, the municipal sewer wastewater treatment facility did not have any requirements for the PFAS levels, so they didn't have any limits. But on the other hand, for example, in the Helsinki, we have two limits: 5 nanograms per liter for PFOS and 5 nanograms per liter for PFOA. So those are limits, but those might not be the relevant limits for the foams that we have, because they are unlikely to be present in modern foams. So would that mean that you could just release it to the sewer? Well, no, you can't, because there is a waste legislation separately. But with the cleaning waters, this might be something that you could consider. And then another consideration that we were really giving into this sprinkler pipe is that if the concentrations are really low, like what sort of cleaning process could be accepted as best available techniques. So just to conclude that because in our case, certainly it's going to be the regional authorities who will be in charge of enforcing the environmental permits, and this would be part of that enforcement and inspection. A lot of technical expertise is going to be required from those authorities when they actually have to figure out whether a company is in compliance with the PFAS legislation. And this concludes my part. here's my email. In case you have some further questions, you can always send them to me directly. But now I would like to open for the remaining 4 minutes. I don't mind if we go longer, but the Q&A. I think we've had a lot of discussions in the chat already. But I know that there are lots of regulatory and scientific experts online, so I kind of would like to hear if you have views on these questions. So if we start from the beginning, there was the question really about how representative these PFAS swab tests could be, because there are all sorts of different elbows and other areas, dents and holes in the tanks. Does anybody have any view on this? I mean, you can just raise your hand, or I think from my perspective, I think it's just this seems to be the only way to evaluate what might have been left in the tank for the time being, even though it clearly has its faults, and you could take the sample from a place that would not be representative for the whole tank, and this how you could get lower results. But okay, I don't see any. Well, we can just review these questions anyway. And there was I think Jaakko already replied to the question whether the high pressure was done inside the tank itself. I understood that the military truck tank was so small that it was even difficult to get the surface swipe sample. Do you want to comment on this, Jaakko?
Yes, we did pressure both of the tanks outside of the tank, so we didn't have to enter inside the tank, if that was the question. And of course, in military truck, it would have been impossible. But both tanks were pressure washed outside, from outside.
Yeah, so the pressure was done on the inside from the outside.
Yes.
Perfect. And then we discussed about these concentration limits that we have in the EU, coming from both the POP regulation as well as the REACH regulation, which was just recently. Then those kind of give us the limits that we need to operate within. And there was a question of glycol improving the mobilization of 6,2-FTAB or 6,2-FTSA. And I think Jaakko already replied to this, that it was not really clear whether it was the glycol that was improving the removal of the PFASs or whether it was just a second rinsing. And then there was a question about the foam bladder tanks. Does it have to be replaced or just rinsed? And I think there was both Niall and Jaakko who were of the opinion that they should be better replaced, considering that they are so difficult to clean out. And then there was a question regarding Antti's presentation on the estimated cost for the whole process, water sampling, testing, and final treatment. I think this was specific to Antti's water treatment process. I didn't see. Antti, did you?
Okay, I've missed the question, but I would say that we are on a level that is approximately maximum 50% of the high temperature incineration, if we consider all costs.
And the high temperature incineration would be around €1 plus per kilo, plus transportation costs, I suppose, like 1,200, 1,300 euros per ton. Just a guess. Then there was a question about the Eurofins test method that they were using, and we use Eurofins and specify EPA method 537.1 modified. I'm not an expert on this, but I think we had a Eurofins representatives online as well. Are you, or is Jaakko able to?
Yeah, I already answered to the question. So
okay.
Eurofins informed that they use this DIN 3840742 method. But Patrick, if you are online, so please confirm.
I am
Patrick.
here, yes.
Yeah.
It's been
Perfect.
an excellent presentation.
It was
and
the other
really...
Patrick, the Eurofins.
Oh, sorry.
Patrick.
Patrick from
Well, glad to see that you're there still. Okay, we don't have, but there was a, you did specify the method that in your presentation that was used by Eurofins. Well, you can put it on the chat. We continue considering that we are running a bit over time already. And then there was info requested on the proprietary resin. Yes. And then there was I don't understand the question by Dauren, but maybe if somebody from FREDSense does that. I'm guessing from the figures, Fred seems to close to UV-VIS methods. With this assumption, I wonder whether the reads are for anionic surf in general or for PFAS surf only. I think this is to Blake or any of your colleagues.
Yeah, absolutely. So I'm reaching out to my technical team as we speak, because honestly, that's a little more in depth than my knowledge. However, someone will have a bit of a better understanding with that than I do. So we'll reach out either in this chat or after the presentation to give that one a real good answer.
Thank you very much. And now we are getting close to the final comments, but this was really an interesting question by does the FREDSense allow an accepted ATSM standard or equivalent that is accepted by government or agency authorities to demonstrate clean? Similarly, how is this field screening viewed by regulators? I think I've already touched upon the same issue that in our case it would be up to the regional authorities to decide what they request and what they accept. I think a lot of it would come to the question of whether you have documented actually a process for cleaning and that it's reliable. And then you have some documentation that would actually show that something also happened, but whether you require a target analysis or TOPA or FREDSense, it's up to the individual authorities. I don't know. We don't have that much experience yet on these results, so I guess that's one reason why we don't know what people think.
Yeah, and I think just to add to that, Timo, I think we're pretty early in the process of working with the regulators. Like you mentioned, it's an ongoing thing, and so I don't think we ever plan to replace lab analysis. Our kit will never be as accurate as a lab. However, it's a useful indicator for an operator on site to actually be able to make some sort of decision, data-backed decision, when they're working in real time, rather than having to, kind of leave site or come back later to a project that's happening right now.
Yeah, if I may comment from sort of like contractor point of view, that okay, if I would be there cleaning the waters, then I'd prefer using on-site method in parallel to the lab analysis, but maybe in a way that I have a first treatment train that will do the actual job, and then I have a backup filter, and I use the online tool to measure between the actual and the backup. So I all the time I know that my final effluent is clean, and then collect parallel lab analysis data on that. So I need no, because there's no coming back. When I've treated the water and I discharge it, it's gone. So that in that way, it's a useful tool. And then still later on, you can verify the on-site data with lab analysis data.
All right. Then we have an interesting question about the detection limit, whether you are working to make it lower at FREDSense, and the requirements here are 4.4 parts per trillion of PFOA equivalents and 0.65 ppt for PFOS, which are pretty low. I think these are like drinking water standards.
Yeah.
Do you want to comment on this?
So, single-digit PPT is difficult even for a lab-based total method. So it's something that we're definitely working on our detection limit, and pushing all the way down to single-digit PPT is a big challenge. We'd love to tackle it, and we'll just kind of continue working on our technology and push that detection limit as low as it can go, while being able to still provide that real-time data to those who can use a sensor at, you know, a 1 or an 1,000 nanogram per liter limit.
Thank you. And then I'm sort of running towards the end here, but I'm just picking up what has not been replied yet. But I just want to highlight the comment from Patrick van Hees from Eurofins that the lab tests they have performed show that on flat stainless steel surfaces, 3 wipes have an overall recovery of 90% for PFAS and 6.2 FTAB. And there is a link where you can get a white paper on that. I think all of the other questions have been replied. Now we are 8 minutes late, but if anybody has any questions or comments, now is your time. Nevertheless, I will just mention that you will receive in your email that you have given during the registration, you will receive the link to the recording, and also the presentations I will send in that same email. It will take a couple of days probably before I get it on our institute website, where it's going to stay for about 2 weeks before our communications department will remove it because there is no subtitles. So if you don't have any further questions, I would like to thank everybody who came to this event. I think we had a great crowd from all over the world on different sorts of experts, and I really hope that we would have this sort of, maybe we should have to organize another discussion event where we could just discuss issues that we have touched upon at this, because these are something that there is so little experience, and for example, there is relatively little analytical data that has been publicly made available, so that you could actually see what kind of concentrations you get from different foams and different rinsing processes. So transparency is probably useful for all of us. But if not for anything else, thank you very much, everybody. You will hear from me in a couple of days.
Timo, are we going to share? Yes, are we going to share these presentations somewhere?
Yeah, I will send them. Well, I will actually put them on the registration website, or I will send them by email. I will see how large they would be, but I will likely send them by email, because that's always easiest, and so many people haven't necessarily gone to the registration site. Okay, thank you. Have a good evening or day or morning or good day.
Thank you.
Thank you.
Timo, thanks everyone.
Thank you.